Welcome back to Inorganic Tutors Institute. In today's lecture, we are going to solve about 20 questions in Advanced Calculus 2. Okay, so our first question is, we want to find a vector that represents the curve of intersection of this plane, okay? And the elliptic cylinder s squared plus 4y squared equals 4. All right, so with this kind of question, first of all, if you have a plane and you have an elliptic cylinder and you want to find a vector that represents the curve of intersection, then first what you have to do is to express the elliptic equation, okay? Express the elliptic equation in the standard form, all right? Then compare with the cos and the sine, right? So what I try to say is s squared plus 4y squared equals 4, right? So here we express this equation in terms of the elliptic, right? In the form of the elliptic equation, right? So here we're going to have s squared over 4 plus y squared over what? 1 equals 1, right? And this can be expressed as s squared over 2 squared plus y squared over 1 squared. And that is equal to 1, right? And this is basically in the form x squared over a plus y squared over b equals 1, right? So this here can be, we can say that our x should be equal to 2 cos t and our y should be equal to sine t, right? We are getting that information from here. You know, this is because of these two, we are going to have the 2 multiplied by the cos, right? So we have 2 cos t and then this is 1. So it's going to be 1 times sine t. So that is what we have here, right? So now we have x and y. Okay, what do we do with this? We substitute this x and y into the plane, right? So we do that here. X plus 2y plus 4z is equal to 4, right? And now we have x and y. So we substitute here. We're going to have 2 cos t plus 2 sine t plus 4z equals what? 4, right? We are interested in the z, right? Because we want to find the vector that represents the curve of intersection. So we make z the subject, and we're going to have 4 minus 2 cos t minus 2 sine t, right? So we divide here by 4, divide here by 4. So we're going to have our z to be 1 minus 2 cos t minus 2 sine t over 4, right? You know, this is 4 over 4. That is why I had the 1. Then we have, you can say that our z is equal to 1 minus cos t plus sine t all over 2, right? So this is what we have for the z. So we have the x component, we have the y component, and now we have the z component. So now we can say that our vector that represents the curve of intersection is given us x, which is 2 cos t, that is 2 cos ti, right? Plus our y is sine tj, right? Plus our z is 1 minus cos t plus sine t all over 2. Then that represents the k, right? So this is the I component, this is the j component, and this is the k component. So that is for question number 1, okay? So this is how you go about questions that are of this form. this is how you go about it. So whenever you have a plane and you have an elliptic cylinder and you want to find a vector that represents the curve of intersection, first express the equation, the elliptic equation, in the standard form. Then use that as your first flow, right? So once you express it in the elliptic standard form, then you compare with the cos and the sine, right? So you know that this, because of this two, is going to be 2 cos t, and because of this one, is going to be sine t, right? So once you substitute into the plane, then you find the other coordinates. So the other coordinates plus this, then you get your vector, right? That is very simple, right? So let's move to problem 2. So with question number 2, you want to evaluate this limit, okay, as t approaches 1 from the positive side. Okay, so let's carefully analyze this. You know, this right here, let's not be bothered about this, the second component either, right? Let's focus on the third component, t cos into 1 over 1 minus t, right? Don't forget that cos oscillates between -1 and +1. So whatever happens here has to be between -1 and +1. So cos into 1 over 1 minus t has to be between -1 and +1, right? Has to be between -1 and +1. So this here, okay, 1 over 1 minus t will deviate this particular problem. So this one, the cos, will make this function not to exist, right? So because of this, this function will not exist, okay? This function will not exist. So that's the limit does not exist. The limit does not exist because of the cos. The cos oscillates between -1 and +1. So because of that, this particular function will not exist. Okay, so that is problem number 2. Let's look at problem number. With question number 3, we want to describe the curve with vector equation r of t equals sine squared cosec ti plus tan cos t all squared g, right? So first of all, we have to identify the components. So with the I component, we say that x should be equal to that, right? Sine squared cosec t. Okay, so with this, we can say that is the same as sine squared times, cosec is the same as 1 over sine, right? So we have 1 over sine t, right? So this is basically, this cancels one of this, then we have sine t. So we have s equals sine t. Okay, so this is what we have, okay, for x. The y component, which is the j portion, is going to be y equals tan t cos t all squared g, right? And you know that tan can be expressed as sine over cos. So we have y equals sine t over cos t times cos t all squared, right? So we have here, this cancels this, and then we have sine t all squared. Okay, so we have y to be sine squared t. Okay, so this is what we have for y, and this is what we have for x. Now we want to describe this particular curve with vector equation, this vector equation. Now this is what we have obtained. So why don't we express this equation in terms of x? Okay, so let's try to express y in terms of what? X. So in doing that, then we can say that y equals what? X squared. right? Because we have sine squared here and we have x equals sine. So if sine is going to, this is going to represent x, then here is going to be what? X squared. So we have y equals x squared. So that is the equation. Okay, so what equation is this? This is basically a parabola, right? So you know how a parabola is. This is just a parabola. Okay, you can have something like this as well. So this is what they have, and this describes a parabola. A parabola. This describes a parabola. Okay, so that is question number 3. Okay, so let's move to question number 4. Number 4, we are given a particular vector valued function, right? And we want to find the direction vector of that particular vector valued function. Okay, so if you have a vector valued function and you want to find the direction vector, first, what do you have to do? All you have to do about that is to differentiate the function, right? So once you differentiate the function, the result becomes your direction vector. So this is our I component. Let's try to take it one by one, right? So our I components will be x. So 3t squared plus 4t all over 2t I, right? So this can be simplified further, right? So we're going to have 3t squared over 2t plus 4t over 2t, right? So this, we're going to have, this cancels one of these t, and we're going to have 3 on 2t plus this cancels this, and we're going to have half, right? So this is the I component. Now this I component, we're going to differentiate this I components, right? So we're going to have x of t, s prime of t to be equal to, when you differentiate 3 on 2t, you're going to have 3 on 2. When you differentiate 1 on 2, you're going to have 0. So this is what we have for the I component, right? So then we move to the j, right? So the j represents our y. Okay, so we have negative into 2 plus t over 2, or j, right? And we know that this can be expressed as negative into 2 on 2 plus t on 2, right? And this is going to give us negative into 1 plus half t. Okay, now this is the j component after simplification. So what do we need to do? We need to differentiate this j component, right? So we're going to have y prime of t to be equal to negative, there is negative here. So when you differentiate 1, you have 0. When you differentiate half t, you're going to have half, but there is a negative here, so it's going to be negative half. Okay, so this is what we have. Then the k component, we can also simplify the k component as well. So we come up here, then we say that k, which is going to be the z, equals negative into 12 minus 2t over 3 here, right? And that is the k component. So we say that z is equal to, this can be simplified further. So we have negative into 4 minus 2 on 3t, right? Then you know that when you differentiate this constant, you get 0. And when you differentiate negative 2 on 3t, you're going to have negative 2 on 3, right? So we have our z prime of t to be equal to negative, there is negative here, right? So negative 2 on 3, right? So we have that to be positive 2 on 3. So that is the z component, right? So the direction vector of this vector valued function is giving us, the direction vector of this vector valued function is giving us r prime of t to be equal to the x is 3 on 2, the y is negative half, and the z is positive 2 on 3. All right, so this becomes our direction vector from the given vector valued function. So r prime of t equals 3 on 2, comma, negative half, comma, 2 on 3. So whenever you are given a vector valued function and you are asked to find the direction vector of that particular vector valued function, all you need to do is to differentiate each component. Differentiate each component, right? Once you differentiate each component, the result you have becomes your direction vector. Okay, so let's move on to problem number. With question number 5, we want to find the parametric equation for the line segment that joins point P of 1, negative 1, and 2 to Q of 4, 1, and 7. Okay, so with this kind of question, once you hear parametric equation for the line segment that joins a particular point to another point, first of all, what you have to do is find the direction vector. Okay, so this is going to help us to do that. Okay, so we find PQ, right? We find PQ. Okay, so PQ will be equal to position vector Q minus position vector P, right? So that is going to be 4, 1, 7 minus 1, 1, 2, right? So we're going to have this minus this is 3, this minus this becomes 2, and 7 minus 2 becomes 5, right? So this is our direction vector. Okay, what are you going to do with this direction vector? We are going to multiply a scalar with this direction vector plus the point, the first point, okay? So this is going to be, our parametric equation is going to be r of t equals p, position vector p plus a scalar times the direction vector, right? So that is the pq, right? So this is going to give us the parametric equation for the line segment. Okay, so we're going to say that r of t is equal to p is 1, 1, 2, and our t is t of what? PQ, and PQ is 3, 2, and 5, right? So in here, what we have to do is to spread this t to all the items in the bracket. Once we are done with that, then we you know what we have to do, parametric equation. So r of t will be equal to 1, 1, 2 plus 3t, 2t, and 5t, right? So this to that, so we're going to have r of t to be equal to 3t plus 1, comma, 3t plus 1, comma, 2t minus 1, then 5t plus 2, 5t plus 2. So this becomes our parametric equation for the lines for the line segment that joins the point P of 1, negative 1, and 2 to Q of 4, 1, and 7. Okay, so that is our parametric equation, R of t of, this is the vector form representation. So this can be represented as 3t plus 1 or I plus 2t minus 1 or j plus 5t plus 2 or k. Okay, so this is the same as this. This is just the vector representation. And this is the position vector representation. So this becomes our parametric equation for the line segment that joins the point P of 1, negative 1, 2, 2, Q of 4, 1, and 7. Right, so that is question number 5. Let's move to question number 6. Question number 6, we want to know the point. At what point is this function, right? Square root of 2t minus 2 all over t 2 minus t comma t squared sine into 1 over t and ln into 2t squared minus 18 can be continuous. Okay, so first of all, if you have a question like this, you want to check for continuity, what you have to know is that, okay, consider them component wise, one by one. Okay, so for me, I see clearly that this one is what going to violate the continuity. So what we have to know is that any argument that is within the ln function or the logarithmic function or the natural log function should be greater than 0. Okay, so we're going to have 2t squared minus 18 to be greater than 0. Okay, so we have 2t squared to be greater than 18. All right, so we have here, we have t squared to be greater than 9. All right, so this means that t will be greater than 3 because we are accepting values that are greater than 0. So we can't consider the negative 3, no, plus or minus 3, but we are going to consider only the positive 3. Okay, so this here should be valid for this. Okay, now consider this square root of 2t, right? This can be greater than or equal to 0 because when you put 0 here, okay, when you put 0 here, you're going to have t to be greater than or equal to 0. So when we have 0 here, you're going to have minus 2 over what? Whatever is here. 0 over whatever it is going to be 0, right? Then we consider this, right? We consider this. So we're going to consider 2 minus t. 2 minus t should be greater than 0. Okay, so this minus must be greater than 0. So we have 2 to be greater than 2, negative t to be greater than minus 2, right? So it means that t should be less than what? 2, right? Okay, then we consider the t squared sine into 1 on t. You know already anything 1 over 0 will be undefined, right? So this here means that we are not going to consider 0. Okay, and this is a product of continuous functions, right? So here we are going to have t to be not t to not be equal to what? T should not be equal to what? 2. Okay, because if t is equal to 2 here, we're going to have 2 minus 2, which is 0, and to make this thing undefined. Okay, and t should not be equal to what? 0 as well. All right, so we can say that 3 will work. So we can say that our solution will be 0 and 0. We're going to consider 3 and what? Positive infinity. This is what is going to make the function continuous, right? Because when you draw the number line, this 2 and this 0, 2, see here, 0 and 2, and then yeah, 0 and 2, and 0 and 3, the intersection is going to be 3 to infinity, right? So we take 3 and infinity exclusive. So this is what is going to make the function continuous, right? This is what is going to make the function continuous. 3 to infinity exclusive. If not because of the ln function or the natural log function, then we could have considered 0 and 2. But because of the natural log function, we are not considering 0. All right. So this is excluded, right? So this is our solution. 3 to infinity exclusive. Okay. So that is our solution for question number 6. Now let's move to question number 7. Okay, so with question number 7, we are given this vector function, and we want to find the parametric equation for the tangent line to the curve at this point. Okay, so if you have a question of this nature, first of all, test the points, okay, and check which of them will be the correct parametric value. Okay, so you test each of these points and see which of them will be the correct parametric value. Once you have that, then you differentiate this vector function to have your direction vector. Okay, so here, let's say that t is equal to pi. Okay, so if t is pi, then when we substitute pi into this, we are going to have what? Negative pi, because cos pi is -1. -1 times pi becomes negative pi. Then here will be pi. When you substitute pi into sine, you have what? 0. Okay, so now let's try to, we know that our correct parametric value is what? Pi. So now let's try to differentiate our vector function t cos t I plus tj plus t sine t k, right? So this here, we are going to differentiate this. Okay, so we differentiate this to have our direction vector. So that will be equal to differential of t cos t. We are going to use the product rule here. So we differentiate t and we have 1, we maintain the cos. So we have cos t, right? Then we maintain the t. We maintain the t, then we differentiate cos, which of course is negative sine. So we have negative sine t, or I, right? Then we differentiate the tj, and that is going to be plus d, right? Then plus differentiate this as well. We are going to use the product rule. So we differentiate t and we have 1, then we maintain the sine t. So we have sine t. Then we differentiate, we maintain the t, then we differentiate sine, of course, is cos, right? Okay. Okay, so this is our direction vector. So we are going to use this direction vector. We substitute pi in place of t. Then we have the value, right? So, or we have the point, right? So we're going to say that r prime of t is now r prime of what? Pi. So it's going to be cos pi minus pi sine pi I plus this place is going to be 1, right? Then this part plus sine pi plus pi cos pi, right? Or j, right? So here we can say that our r prime of pi will be equal to cos pi is -1. So we have -1, then negative pi sine pi is 0, right? You know, sine pi is 0. 0 times pi becomes 0. So we only have negative pi for the I component. Then the j component is already 1, right? It's 1j, of which it's 1, plus the k component sine pi is 0. Then we know that cos pi is -1. -1 times pi becomes negative pi k, right? So this is our direction vector. Now let's convert this direction vector into a point. So we're going to have our point to be, let's say, this, okay? V to be -1, 1, and negative pi. Okay, so now we have the direction vector, the point for the direction vector. We multiply this direction vector by a scalar, right? So we multiply this by a scalar. Then we have into negative t, and negative pi t. Okay, so now we are interested in the what? Parametric equation. So the parametric equation, say r of t will be equal to the point of which we have here, the point, say p, plus the v here, right? So this is going to be negative pi, 0, and plus negative t, and negative pi t, right? So we combine this component, right? So this is going to be negative pi, negative t, and this is going to be pi plus t. Then we have negative pi t. Okay, we are combining them component-wise. So this is negative pi plus negative pi. Negative t becomes negative pi, negative t. So that is the I component. Then the second component is become pi plus t becomes pi plus t. Then 0 plus negative pi t becomes negative pi t. Okay, so that is our parametric equation for this particular question. So our parametric equation is negative pi, negative t, then pi plus t, then negative pi t. Okay, so this is our parametric equation to this particular problem. Okay, so this is question number 7. Let's move on to question number 8. Okay, so this is question number 8. All right, so the question goes, the Cartesian equation of line is, a particular line is x minus 2 over 1 equals y over 5 equals z plus 3 over 4. Okay, and we want to find the vector equation of this particular line. Okay, so how do we get this vector equation? This question, this here, okay, is our x coordinate, right? So x minus 2 equals 0. Then this implies that our x is what? Positive 2. Then this y equals 0 is our y coordinate, and z plus 3 equals 0. Z equals negative 3 is our z coordinate, right? So this and that becomes our point, right? So let's say P, we name it P, right? So we have 2, 0, and negative 3. And the denominator here and here becomes our direction vector, right? So this and that becomes our direction vector. So let's call that V, right? So we have that to be 1, 5, and 4. Okay, so all we have to do is multiply this direction vector with a scalar, right? So we multiply this with a scalar plus this. So we're going to have our vector equation to be 2, 0, -3 plus t into 1, 5, and 4, right? So we have our vector equation to be 2 plus t, right? Then this will be 5t. Here will be what? 0. So we're going to have 5t. And this is going to be 4t plus -3. So we're going to have 4t minus 3, right? So this becomes our vector equation. But this expression can be expressed in a different format, right? So we can say that this is the same as t power 4 t squared minus 4 over t minus 2, and this is the same as 10t over 2, and this is also the same as 12t squared minus 9t over 3t. Okay, when you break this is difference of two squares, right? So when you break this down and you cancel out, you get back to this. When you cancel this out, you get back to the 5t. When you cancel this out, you get back to this. So this is our vector equation to this particular problem. Okay, so whenever you have a Cartesian equation of a line and you want to find the vector equation, your numerator x, y, and z becomes your point, and the denominator becomes your direction vector. Once you have these 2 points, multiply the direction vector by a scalar, okay? Then add it to the point, have your vector equation, and that is it. Okay, so let's move to, okay, so this is question number 9. Okay, we want to find a unit tangent vector along this curve. Okay, so back when you look back, if you want to find a particular unit vector, it's basically the position vector over the magnitude of the position vector, right? So this is from pre-calculus. Okay, in here, because we have tangents involved, then that is going to be the differential of the curve, right? And this is radius, okay, over the magnitude of what? The differential radius. So this is how we find the unit tangent vector in here. Because of the tangent and because it is a curve, we have to find the differentiation, the differential of the curve. Okay, so this is what you are going to do. Okay, so first of all, we need the differential of this, right? So differential of that will be equal to, we know you differentiate e to the t, and that remains the same. They maintain the cos 2t. Then we differentiate cos 2t, right? Differential of that becomes -2 sine 2t, right? So we have -2 sine 2t e to the t, right? So that is the first component. The second component, we apply the product through the same principle. Okay, so we differentiate e to the t and it remains the same. Then we maintain the second function. Then we differentiate sine 2t, and that becomes cos 2t, right? So plus 2 cos 2t e to the t. Okay, so this is our differential to this particular function. Okay, so what do we need? That we need the magnitude of this. Okay, so the magnitude of this will be equal to square root of e to the t cos 2t all squared plus -2 sine 2t e to the t all squared plus e to the t sine 2t all squared plus 2 cos 2t e to the t all squared, right? So here, what you are going to do is just simplify what is under the square root sign. So we have that to be equal to square root of e to the 2t cos squared 2t plus 4 sine squared 2t e to the 2t plus e to the 2t sine squared 2t plus 4 cos squared 2t e to the 2t, right? So this is what we have under the square root sign. So you can see that this and this can be common here, and yeah, this and that. 4 cos squared 2t and 4 sine squared 2t can be factorized into 1, right? So we're going to have r prime of t, magnitude of that is equal to square root of this, and this will go to one bracket, right? So we have e to the 2t cos squared 2t plus e to the 2t sine squared 2t plus 4 sine squared 2t e to the 2t plus 4 cos squared 2t e to the 2t. Okay, so you see what we have now. So this means that we can factorize e to the 2t out here, and in here too we can factorize 4 e to the 2t out, right? So we're going to have r prime of t, magnitude of that will be equal to e to the 2t out. Then we have cos squared 2t plus sine squared 2t plus 4 e to the 2t out. Then we have sine squared 2t plus cos squared 2t, right? So the work is getting interesting, right? So we're going to have r prime of t to be equal to square root of, this is an identity, right? This is going to be 1, and this is also going to be 1. So we're going to have e to the 2t into 1 plus 4e to the 2t into 1. Okay, so here we can, let's go up. Okay, so we take off this here. Then we say that our magnitude of the differential radius will be equal to square root of, when you simplify this, you're going to have e to the 2t plus 4e to the 2t. Okay, so this can be simplified further to have 1 plus 4 is 5 e to the 2t. Okay, so this is what we have, and you know that this is mathematically correct, right? E to the 2t. Okay, so furthermore, we say that the magnitude of the differential radius will be equal to square root of 5 times square root of e to the 2t. And you know that square root of e to the 2t is the same as e to the 2t, square root of e to the 2t, right? So this cancels this, and then we have e to the t square root of 5. Okay, so this Okay, so this is what we have now as the magnitude. So as usual, we say that our unit tangent vector will be equal to the radius, the differential radius over the magnitude of the differential radius. So we are going to have, this is the differential radius. Okay, so we're going to have e to the t cos 2t minus 2 sine 2t e to the t all over the magnitude, right? E to the t square root of 5. That is the first component, right? Then the second component will be, so this is the I. Then the j component will be e to the t sine 2t plus 2 cos 2t e to the t all over square root of 5 e to the t, right? So this is what we have. Now, this can be simplified further, okay? So we simplify that. Then we have our unit tangent vector to be equal to, this cancels this, and this as well cancels this, right? You know, we factored this out, and then we factored this out here as well. So this cancels this, and this cancels this as well. So in here, we're going to have cos 2t minus 2 sine 2t over square root of 5, I component, then plus sine 2t plus 2 cos 2t all over square root of 5j, right? And you know that square root of 5 can be expressed as square root of 5 square root of 5 over 5, right? So we're going to have cos 2t minus 2 sine 2t times square root of 5 over 5i, okay? Or you can decide to bring that forward. So we have square root of 5 over 5i plus we have sine 2t plus cos 2t square root of 5 over 5j. So this becomes our unit tangent vector. This becomes our unit tangent vector to this particular curve. Okay, so that is the end of problem number 9. Let's move on to question number 10. So with question number 10, we have this moving particle, okay, that starts at initial position r of 0 equals this, with initial velocity v of 0 equals this, right? And we have the acceleration, okay? Now we want to find the position at time t. So this information will make it clear, or make it easy to find the position at time t. Okay, so first of all, we integrate the acceleration, okay, component wise, okay, to have the velocity. So that is going to be component wise, okay? So we integrate the I component, and that is going to be, when you integrate for t, you're going to have t squared over what? T squared, 4t squared over what? 2, right? Plus a constant, say c1, okay? And that is the I component. So this is basically equal to 2t squared plus a constant, say c1. So this is the I component. Then we come to the j component, 6tj. So when you integrate that, you're going to have, you're going to have 6t squared over 2 plus a constant, say C2. Okay, so this is going to be 3t squared plus C2. So this is the second component. Then the last component, which is the k, when you integrate k with respect to t, you're going to have t. So the last component will be equal to t plus a constant c3. Okay, so this is what we have for the velocity, the I component, the j component, and the k component. Okay, so now we are going to look for this constant c1, c2, and c3. And that this position vector, this initial velocity, will help us to find the c1, c2, and c3. So we say that v of 0 should be equal to if v of 0, right? So first of all, our 2t squared plus c1, our c1 will be what? Our c1 will be what? 1, right? So this plus the second component, 3t squared plus c2 plus the third component, t plus what? c3. And this should be equal to what? The initial velocity, 1, 0, 0. No, this is the initial velocity, 1, -1, and 1. Okay, so this is what we have. Okay, this is what we have. So let's say this, we are using the angle bracket. So this to this, this to this, and this to that. Okay, so now we can say that our velocity will be equal to 2t squared plus 1. Okay, c1 is 1, and then the second component is going to be 3t squared plus -1, right? So that will be -1. Okay, then the last component will be t plus +1. Okay, so this is our velocity, 2t squared plus 1, comma 3t squared minus 1, then t plus 1. So this is our velocity. Okay, now we have the velocity. We need the position vector. What do? We integrate again, right? We integrate the velocity, then we get the position for position at time t, right? So we integrate this again. Okay, component wise, to have r of t, right? So that will be equal to, when you integrate 2t squared plus 1, you have 2t cubed over 3 plus t, right? Plus a constant, say c, let's use d1, okay? d1. Then the second part will be 3t cubed minus t over 3 here. So this is going to be 3t t cubed minus t, okay? Then the last part is going to be t squared over 2 plus t. So don't forget your constant, d2, d3. Okay, so we are going to find the constant, right? The constant in here using the initial values. So we're going to use the initial values to find the constant. So we say that r of t will be equal to, now we compare that, 2t cubed over 3 plus t plus d1, and then t cubed minus t plus d2, and then t squared over 2 plus t plus d3 here. And this should be equal to the initials, right? Okay, so basically you can see that our Our D1 is what? 1. Our D2 is 0, and our D3 is also 0. So we can say that our position at time t, will be equal to 2t cubed over 3 plus t plus 1. Okay, then the second component will be t cubed minus t, comma, t squared over 2 plus t. Okay, so this will be our position at time t equals at time t. Okay, so this is the angle bracket, the expression in the angle bracket form. So we can leave it this way in the position vector form. So we say 2t cubed over 3 plus t plus 1, or I plus t cubed minus t, or j plus t squared over 2 plus t, or k, right? So this is our position at time t. Okay, so first of all, if you have a moving particle, okay, at a starting point with initials, right? Initial position vector to be this, and you have the velocity, the initial position, the initial velocity, right? And you have the acceleration. First of all, integrate the acceleration to get the velocity. Then, but the focus is integrate it component-wise so that you have each and every one with a constant, okay? So with that, you can find your constant using the initial velocity. Once you have that, then you integrate the velocity to also have the position at time t. Then you compare that with the initial positions. Then you have the original equation. Okay, so that is what we have here for question number 10. This is a problem that we have for question number 11. Okay, so we want to integrate this particular function. Okay, this is the integration that we have. Okay, we want to evaluate it. So what we do, first of all, note that this here, we can integrate it component-wise. So let's try to integrate them component-wise. So t squared e to the negative t dt. Okay, so we pick this, we integrate. After that, we do this, we do that. Okay, so first of all, when you want to integrate two functions that are multiplying or product of two functions, use the product rule. Okay, use the integration by parts, right? So here, let's try to use the tabular method, okay? The DI method. So here, our u, which is the differential function, will be t squared, and the integration function will be e to the negative t. So we have v here. Okay, so t squared e to the negative t here. Now, we differentiate this to, we have a constant, right? So we have 2t here. We differentiate again, we have 2. We differentiate again, we have 0, right? Here, we integrate the v, then we have negative e to the negative v. Then we come here, we have positive e to the negative v. Then we come here, we have negative e to the negative v. Okay, so this is by part, okay? So we are going to combine it. Okay, we are going to combine it. Okay, so this goes here, this goes here, this goes here. Okay, so it's plus minus plus. Okay, here it's going to be t squared negative t squared e to the negative t squared, negative is here, so negative t squared e to the negative t. Then this and this, there is negative on the arrow, right? So you're going to have negative 2t e to the negative t, then 2 times negative of this, right? So it's going to be negative 2 e to the negative t. Okay, so this is what we have for the first part. Okay, so we have negative t squared e to the negative t is common, right? So we can factor that out. Okay, so we factor that out, e to the negative t out, then we have negative t squared minus 2t minus 2 in here. Okay, so this is what we have for the I component. So we consider the j component as well, then we integrate. So with the j component, we have 1 over t squared minus 1, right? We want to integrate this. Okay, so this we have to use the integration, the partial integration by partial fractions, right? So in here we can see that this 1 over t squared minus 1 is equal to 1 over t minus 1, then t plus 1, right? So this is equivalent to a over t minus 1 plus b over t plus 1. Okay, so now that we have this, then we can go ahead and say that, 1 over t squared, right, is equal to a over t minus 1 plus b over t plus 1. Okay, so we are looking for the unknowns, then we go and substitute and integrate. Okay, so here we're going to have t minus 1, t plus 1. Okay, so we're going to have a into t plus 1, then b into t minus 1. Okay, so this will be equal to a into t plus 1, b into t minus 1 equals 1. Okay, so we want to find the unknowns. So our t should be equal to negative 1 so that this will go to 0. And then we have negative 2b equals 1. So this implies that our b will be equal to what? Negative half. Okay, then we say that t should be equal to what? Positive 1 as well, so that this also goes off. So we're going to have a into 2 should be equal to 1. So this implies that our a is positive half, right? So we have the unknowns a and b, half and negative half. So we substitute here, then we go and integrate. So this is now equal to integral of 1 over 2 into t minus 1 plus 1 minus 1 over 2 into t plus 1, all the t, right? So we're going to integrate that. So we integrate this, okay? So when you integrate 1 over 2 into t minus t, you're going to have ln half ln into what? T minus 1, that is absolute, minus half ln into t plus 1, right? So this is what we have. And don't forget that in logarithm, when you have negative, then it means you are dividing. So we divide this log, we factor up half out, right? Then we say that this will be ln into t minus 1 over, or we can say that because the lane is common to all, we say that half lane into t minus 1 over t plus 1. Okay, so this is the second component, okay? And this is the first component. So we go ahead to the third component where we have t squared over 2 minus 1. We want to integrate this, right? So we're going to integrate this. Integral of t squared over 2 will be t cubed over what? 6, right? Minus t. Integral of -1 is minus t with respect to t, okay? So this is what we have for the third component. So now we can combine this, we can combine this, we can combine that. Okay, that is very interesting, right? So now we can say that our solution, okay, so let me write the third component at this point. T cubed over 6 minus 1, t cubed over 6 minus t as our third component for this, right? And let's try to do this. The first component, we can write it as negative e to the negative t into this is a quadratic function, right? So once we factor out the negative, it means that this part will be positive, this part will be positive, right? So we can say that this is a quadratic function, right? So that can be expressed as t plus 1 all squared plus 1, okay? Okay, so this in here can be expressed as this. This, when you expand it, you have t squared plus 2t plus 1 plus 1, then you get 2. Okay, so this is what we have for the I component. Then we come to the j component. Okay, so we add it to the j component plus half lane into t minus 1 over t plus 1. Okay, so this is the j component, okay, plus the k component, which is we have here t cubed over 6 minus t, and this is the k component, right? So this becomes our final answer to this particular integral. So don't forget your constant of integration, c. Okay, so this is the final answer to this particular problem. This is the final answer. So this is application of pre-calculus and this advanced, right? So don't forget your partial differentiation. If you forget about that, watch out. My link is below at the description on integration by part, integration by partial fractions. You learn all that to recap whatever you lost, right? So that you can catch up with advanced, right? So in here, we use by partial fraction and we use by parts, and this help us to evaluate this integrand, right? So this is the solution to this particular problem, and that is question number 11. So we move on to question number 12. So with question number 12, we want to find the arc length of a parametric curve defined by this, right? Okay, so first of all, you know what, if you want to talk about arc length, then you have to think of this integral of from a lower limit to upper limit, then the magnitude of the differential radius, right? The magnitude of the differential radius dt, right? So we need all this to be able to finish up this problem. Okay, so first of all, we find the differentiation or the differential of the radius, right? So we're going to have differential of this function, and that is going to be differential of course is of course negative sine t. Differential of sine is cos, right? So we have cos t, and differential of ln into cos t will be negative, right? So we have, differential of any function, any argument in the ln is 1 over the function in the ln times the differential of the function, right? So this here, when we differentiate this, we're going to have 1 over cos times differential of cos, which is negative sine, right? So, and you know that negative sine over cos is tan. So we have negative tan, right? So this here is going to be negative tan t. Okay, see the something. So don't forget your basic calculus. Okay, so this is the differential. Okay, so we're going to find the magnitude of this. Then we can proceed, right? So the magnitude of that will be equal to square root of negative sine t all squared, negative sine t all squared plus cos t all squared plus negative tan t all squared, right? So in here, we're going to have this will be equal to square root of sine squared t plus cos squared t plus tan squared t, right? Don't forget that this is an identity, a standard and well-known identity. So we're going to have square root of this here is 1 plus this here will be what? Tan squared t. And don't forget that in earlier notice, I said that tan is equal to sine over cos, right? So we're going to put that here. Then we have square root of 1 plus sine squared t over cos squared t. Okay, so let's try to avoid the fraction under the square root sign. So that is going to be square root of, so we multiply here by cos squared t. So we have cos squared t plus sine squared t all over cos squared t, right? So again, we have 1 at the numerator. So we can say that the magnitude of the differential radius will be equal to square root of, now this is 1, okay? So we have 1 over cos squared t, right? And you know that cos, okay, 1 over cos is what? Sec. So don't forget 1 over cos is equal to what? Sec. Okay, so this can further be simplified to have 1 square root of 1 over square root of what? Cos squared t. Okay, so we're going to have the magnitude of the differential radius to be equal to square root of 1 is what? 1 all over square root of cos squared t becomes cos t, right? So we have cos t. Great. And don't forget that 1 over cos is what? Sec. So we have sec t. Okay, so this becomes our magnitude. Okay, so this is the magnitude of this differential radius. So once we have the magnitude, then we can go ahead to find the arc length, right? So from a lower limit to upper limit of the magnitude of the differential radius dt, right? So we're going to put this here. and integrate from 0 to what? Pi on 4. So we're going to have from 0 to pi on 4 of what? Sec t dt. So now the work is so easy, right? So we're going to have integral of sec is ln into sec t plus what? Tant, right? So we're going to have ln into sec t plus tant t, right? Plus a constant, okay? But this is a definite integral, right? So there is no need for a constant of integration over the limit 0 and what? 0 to pi. Okay, so don't forget, integral of sec is ln into sec t plus what? Tant t. So we are going to use this limit, okay? So here, we're going to do it one after the other. Okay, so we take the upper limit, we substitute, then we're going to have, don't forget as well that sec t is 1 over cos, so we are going to use that to do the evaluation. Okay, we are going to use that to do the evaluation. So with that, we say that we are doing the evaluation right from there. So sec t is the same as 1 over what? Cos t. Okay, so we substitute the pi on 4 in it, and it's going to be 1 over what? Cos pi on 4. And you know that pi on 4 is what? 45. And cos 45 is basically square root of 2, right? Cos 45 is square root of 2 over 2. Okay, so we have 1 over square root of 2 over 2, and that is equal to square root of 2. So when you substitute pi on 4 into sec t, you have square root of 2. Okay, so once we have that, then we can substitute as well into tant. And you know that tant is sine over cos, right? So sine over cos, and you know that tan t is the same as sine t over what? Cos t, right? And sine t, when you substitute pi on 4 into sine t, you have square root of 2 over 2, and the same as cos 45, right? So you have cos pi on 4, and that is the same result. So we have square root of 2 over 2, and this is equal to 1. So tan pi on 4 is positive 1. Okay, so we are done with the first part. Now let's go to at t equals 0. Okay, so at t equals 0, sec 0, of which is 1 over cos 0, is what? Positive 1. Okay, so we have that part to be 1. So at t equals 0, we have sec t, which is equal to 1 over cos t is equal to 1 over what? Cos 0. And cos 0 is what? 1. 1 over 1 is 1. Now, times t, at time t equals 0, we have what? Sine 0 over cos 0. Cos 0 is 1, and sine 0 is 0, right? So we have 0 over 1, and that becomes 0. So we have 0 here, right? So now we're going to subtract this plus this, then this plus this here. So we're going to have our length to be equal to ln into square root of 2 plus 1 minus ln into 1 plus 0, right? 1 plus 0. And that is basically going to give us, ln into square root of 2 plus 1 minus ln 1 plus 0 is 1, and ln 1 is what? 0. So we have minus 0. Okay, so our length will basically be equal to ln into square root of 2 plus 1. Okay, ln into square root of 2 plus 1 is the same as square root of 0.77. Okay, so this is the final answer to the problem. Okay, so our arc length is equal to ln into square root of 2 plus 1 here, square root of 2 plus 1, and this is the same as square root of 0.77. Okay, that is very interesting, right? So follow the procedure step by step and you get to understand all this. Okay, so now let's move on to question number 13. Okay, so this is question number 13, right? You want to find the directional derivative at the point 1, 1, pi on 4 in the direction p of 2, 1, 2, 2, q of 3, 2, and 5. Okay, so this is very simple. Okay, first of all, what you have to do is find the direction vector, the unit vector in the direction of v, or in the direction of the velocity. So here we use this point, right? So pq, okay, so that would be q minus p, right? And that is equal to 3, 2, 5 minus 2, 1, 2. Okay, so we're going to have that to be 1, 1, and 3. Okay, so we have this. Okay, so this is our initials. Okay, so we find the magnitude of this position vectors. Okay, so the magnitude of this, let's say this is v. Okay, so the magnitude of this will be equal to what? Square root of 1 squared plus 1 squared plus 3 squared, and that is equal to what? 1 plus 1 plus what? 9. And this is square root of what? 11. Okay, so we have square root of 11 for the magnitude of the vector. Okay, so once we have the velocity, the vector, the magnitude of the vector, and the position vectors, then we find the unit vectors in the direction of what? The v. So unit vectors in the direction of v. Okay, so that will be equal to this, right? So 1, 1, 3 over square root of what? 11, right? So once we have that, then what we need is the gradient of the function. Okay, once we have this, what we need next is the gradient of the function given. Okay, so we find the gradient of this function given at this point. So we're going to differentiate this function partially with respect to x, y, and z. Then we substitute the points inside to find the gradient. Once we are done with that, then we dot them, right? So we're going to find the gradients at these 3 variables, right? So the gradient, we're going to differentiate partially with respect to x, y, and z. So fs will be equal to, differentiate this function with respect to x is going to be y sine z e to the x sine e to the xy sine z, right? Then with respect to y will be equal to x sine z e to the xy sine z, and with respect to z will be equal to, with respect to z means we are differentiating the sign, right? And that's cos, right? So we have cos z e to the x, y, sine z. Okay, so this is what we have for the differentials. So what we need to do, okay, so now that we have the derivative with respect to x, y, and z, we substitute the point inside to find the gradient. Okay, so fx at the point 1, 1, pi on 4 will be equal to, when you substitute this point inside, you're going to have sine pi on 4 is square root of 2 over 2. So we have square root of 2 over 2 e to the same thing, square root of 2 over 2. Then the same thing applies here because of the 1, 1, 1. It will remain the same thing. So we have fy of 1, 1 pi on 4 to be equal to square root of 2 over 2 e to the square root of 2 over 2. Then fz will be 1, 1 pi on 4 to the square root of 2 over 2 square root of e to the square root of 2 over 2. Okay, so this is what we have. Now we can say that our gradient of which is this will be equal to square root of 2 over 2 e to the square root of 2 over 2, comma, square root of 2 over 2 e to the square root of 2 over 2, then, comma, square root of 2 over 2 e to the square root of 2 over 2. Okay, so this is what we have. Now we can say that this, because they are all the same, we factor this out. Then we factor this out. Then we have into 1, 1, 1. Okay, they are all the same. So we factor that out. Then we have 1, 1, 1. When you multiply back, you have the same thing. So this is our gradient. So we multiply the gradient with the direction, unit vector in the direction of what? The vein. So we multiply this and this, that is the dot. Then we have the directional derivative. Okay, so that is how we find the directional derivative. Okay, so we're going to dot this with this. Okay, so will be equal to 1 over square root of 2 over 2 into 1, 1, 1 times square root of 11, 1 over square root of 11 times 1, 1, 3. Okay, so we are taking the dot. Okay, so this square root of 2 over 2 times 1 over square root of 11, and that will give, right? So this is basically equal to 5 over square root of 22 over 5 over square root of 22 e to the square root of 2 over 2. And square root of 2 over 2 can be expressed as 5 over square root of 22 e to the 1 over square root of 2. Okay, so this becomes our final solution to this particular problem. Okay, so this is how you find the directional vector, the directional derivative. The directional derivative. First, find the unit vector in the direction of the velocity, right? So you find your unit vector if you are given the point, okay? If you are given the point, then what you have to do is find the difference, okay? then you have your position vector. Once you have the position vector, find the magnitude of the position vector, then divide it by the position vector. Then you have your unit vector in the direction of the velocity. Once you are done with that, then you find the gradient. Okay, so the gradient, you have multiple variables. So we find with respect to each variable. Then when you are done, you substitute the points inside. Okay, then you evaluate. Once you evaluate, then you dot the two, the unit vector and the gradient, to have your directional derivative. Okay, now if we talk about the maximum directional derivative, that is basically the magnitude of the gradient. If you talk about the maximum directional derivative, that one you not go this far. Once you have the gradient, you find the magnitude of that, and that becomes the maximum directional derivative. Take note. Let me mention it again. If you ask for directional derivative, then you find the unit vector in the direction of the velocity. So if you have these 2 points, find the difference, find the position vector. Once you have the position vector, find the magnitude of that, then you can know the unit vector out of that. Once you have that, then the function that you have been given, find gradients for that, then you substitute the points to have the evaluated points. Okay, the evaluated gradient. So once you have the gradient, you multiply it by the unit vector to have the directional derivative. Okay, so that is with regards to directional derivative. But if you ask for maximum directional derivative, that one you not go this far to dot the unit vector and the gradient. What you have to do is find the gradient. Once you have the gradient, substitute the points and then find the evaluated gradient. Once you have that, find the gradient of that. The gradient of the magnitude of the gradient will result into the maximum directional derivative. And that is today's particular question, question number 13. Now let's move to question number 4. All right, so with question number 14, we have to find r of t, right, such that r prime of t is equal to this function. Okay, you know the r prime of t is the derivative of what? The r of t. So now we want the r of t, so we need to what? Integrate. Okay, and we have been given the initial position for r of t. So we have r of 0 equals half I minus 3j plus 4k. So we just need to integrate this r prime of t to get r of t. Then we equate each component to this and this and that. Right. So here we are going to integrate r prime of t with respect to t equals e power 3t plus 1i plus 1 plus 2e to the negative 2j plus 2e to the t minus 1k, right? You know what? We have to integrate them component-wise, okay? So we are going to integrate the I component, we integrate the j component, then we integrate the k component, okay? So first of all, let's start with the I component. So with the I component, we're going to have integral of e power 3t plus 1 or I, right, dt, right? And that should be equal to, when you integrate e to the 3t, you are going to have e to the 3t over 3, right? You differentiate the function on e, then use it to divide the e to the 3t, and you have e to the 3t over 3 plus, you integrate 1 with respect to t, you have t, so you have plus t. Then, you know, whenever you integrate a function, an indefinite function, you add a. Okay, so now that we have the integral for the I component, right, of which is this, then we compare with the initial, the I component of the initial what position, right? So we see that r of 0 is equal to e to the 3t over 3 plus t plus c1 should be equal to what? Half, right? So wherever we see, you know, this is I and this is what? I as well. Okay? So wherever we see t, we are going to put what? 0. So wherever we see t, we are going to put what? 0. Okay, so we say that half should be equal to e to the 3 into 0 over 3 plus 0 plus c1 here. Okay, now we need c1. Okay, so this is going to be half equals e to the 3 into 0 will give us e to the 0 over 3 plus c1. Okay, so now we can say that we have half equals e to the 0 is 1. So we have 1 over 3 plus c1. Okay, so we can say that our c1 will be equal to half minus 1 on 3. Okay, so we're going to say that our c1 will be equal to 1 on 6. Okay, so this is what we have for c1. Okay, so we are going to use that. We are going to use that when we want to combine everything. So this is what we have. We are going to substitute here to have the I component, right, of the position. So we say that, let me put that here. So we're going to say that the I component is equal to e to the 3t over 3 plus t plus, now our c1 is what? 1 on 6. So 1 on 6. So this is the I component, right? Okay, that is very interesting, right? So now that we have the I component, we go ahead to find the j components. Okay, so we say that the j component of which we have here, we are going to integrate that. So integral of 1 plus, there is a negative here, okay? So negative into 1 plus 2e to the negative 2t dt, right? So we factor the negative up, so we have negative into 1 plus 2e to the negative 2t dt, right? So here we want to integrate this function, okay, with respect to t. So we're going to say that integral of 1 with respect to t is t, then plus integral of 2 e to the 2 negative 2t becomes negative 2t here over negative 2, right? Plus our constant of integration of which we are going to use c2. So we have negative into t plus, this is going to be negative y, negative, so we have negative 1. So negative e negative 2t plus a constant c2, right? So this is what we have for the j component. So we compare this to the j component of the position, the initial position, right? So we're going to say that where our t is 0, so at the initial position, the t is what? 0. So we're going to say that the negative 3 should be equal to negative into negative into 0 minus e to the what? Negative 2 into what? 0 plus c2, right? So we continue from here. Then we say that we have negative 3 equals negative into 0 plus c2, right? So we're going to have negative 3 equals positive e to the 0 plus c2, right? So here, this is 1. So we have 1 plus c2. Then we have negative 3 here. Now we need c2. So what do? We maintain the c2 here. Then we send this here. We're going to have minus 4. Right? So we say that our c2 is minus. Once we have the c2, we substitute the c2 into the integrand, right? So we're going to have our second component to be e to the negative 2t minus t plus our c2 is negative 4. So we substitute negative 4 here, right? So we have our second component to be this, okay? What we need next is to integrate the last component, right? Which is the k, right? So we're going to integrate 2e to the t minus 1, right? With respect to t, okay? So here we say that this, when you integrate 2e to the t, you're going to have 2e to the t over 1, of which is the same thing, right? Minus, when you integrate negative 1, you have negative 1, right? So we have negative t, right? So plus our constant of integration, of which we are going to use C3, okay? Now that we have the integrand of the third component, we compare it with the initial position for the third component, of which is what? 4, right? So we're going to say that this is equal to what? 4. Okay, so once we know this, then we know that at the initial position, t is equal to what? 0. So we substitute t equals 0. Then we're going to have 2e to the 0 minus 0 plus c3 equals what? 4. Okay, so here we say that we have 2e to the 0 plus c3 equals what? 4. Okay, so e to the 0 is what? 1. So we have 2 into 1 plus c3 equals 4. And then this is 2. We cross it to this side and we have 4 minus 2. We have c3 to be equal to what? 2. So we have our c3 to be 2. So we're going to substitute the c3 into here. Then we have the actual component for the k. Okay, so we substitute that. So we're going to have 2e to the t minus t plus what? The c3 is 2. So we have the k component. Okay, so this is the k component, and this is the j component. This is the I component. Okay, so all you need to just combine them and then you are there. So we say that our r of t will be equal to e to the 3t over 3 plus t plus 1 on 6, right? Or I plus e to the negative 2t minus 4 minus t, or j, plus the last component, which is 2e to the t minus t plus 2, or k, right? So this is what we have for our r of what? T. Okay, so this is how we do it. Very simple. If you have r prime of t and you want to find r of t, given the initials for the position or the initials for the r of t, what you need to do is just integrate each component, right? Each component of the r prime of t to have the r of t. Then once you are done integrating, let's say I components, compare that to the I component of the initial position, right? So if you do that, then you say that, don't forget, at the initial position, t is equal to 0. So once t is equal to 0, you will be able to find your constants. And once you are done finding the constant, you substitute into the integrand. Then you find the actual component for the I. Good. You do same for j and k. Then you combine them to have your r of t. Okay, so now this is question number 14. Let's move on to question number 15. All right. So with question number 15, this is what we have. We have u of t equals this function and v of t equals this, okay? And we want to find the derivative of u of t cross v of t with respect to t. Okay, so first of all, what I want you to understand is that whenever you have cross products, what you have to think about is use the product rule to deal with it, okay? So this here, we know that d with respect to t of u of t cross v of t will be equal to, product rule says that differentiate the first term, maintain the second term, plus maintain the first term, differentiate the second term. Please don't misposition this. Once you misposition this, you are going to have a wrong answer. Don't forget that this you are going to apply matrices, okay? And matrices really appreciate order. The man of matrix, Carl Friedrichs Gosh, he really appreciates order. So don't change the position of the differentiation, okay? So this is equal to you differentiate the first term, so u prime of t cross v prime of t. So we differentiated the first term, maintain the second term, plus we maintain the first term, then we differentiate the second term, right? So that is the product rule. So once you are able to do this, the rest is computations, okay? You have to be very careful with your computations because you are going to use matrices, okay? So we have u prime of t cross v prime of t. So this means that we need u prime of t and we need v prime of t because we already have u of t and we already have v of t. So we have to find u prime of t, okay? So u prime of t basically means that we want to differentiate the u of t, right? So u prime of t will be equal to, we differentiate t and we have 1, right? We differentiate e to the t and we have e to the t. You differentiate t squared and you have 2t, okay? Then we find v prime of t, right? And that it will be equal to differentiate cos and you have negative sine. So we have negative sine t. And then you differentiate sine and you have cos. So we have cos t. Then you differentiate the constant, you have 0. So you have 0, okay? Great. So once we have u prime of t, we have v prime of t, and we have u of t, and we have v of t, the rest is matrices. Don't forget, order is very important. So here we are going to find u prime of t cross v prime of t. So we say that u prime of t cross v of t will be equal to, we are applying the matrix, right? So we have I, J, K, right? Then we come here. Where is our u prime of t? Our u prime of t is this. So we're going to say 1 e to the t and 2t, right? Then where is our v of t? Our v of t is cos t and sine t and 1, right? So we have this, we have that here. So this we have to use, we need to simplify this, okay? So we are going to say that we are using the first rule, okay? We are using the first rule. So I into, then we maintain this. Once you take this, you cancel everything on that rule, cancel everything beneath that element. So we're going to have this. So we have e to the t, 2t, sine t, and 1, right? Minus, we take this, we cancel everything under it, then we cancel everything on that rule. So we're going to have into 1 cos t and 2t and 1, right? Plus k, okay? K, we take k, we cancel everything on that rule, cancel everything under it, right? So we're going to have 1 cos t and e to the t sine t, right? So this is what we have. So let's break it down. So we're going to say that this times this. So right, you have I into e to the t minus this times this 2t sine t, right? Then minus j into this times this is 1 minus this times this is minus 2, right? Minus 2 cos t, right? So we have the j component left with the last component with the k, right? So let's write that here. So we have the k, of which k into sine t minus e to the t cos t, right? So this is the k component and this is I and j. Okay, so can we simplify that? Let's leave it that way, right? Let's leave it that way. Or we can spread we can spread the I through them. Then we're going to say that we have e to the t I minus 2t sine t e minus sine 2t I minus j plus 2t cos t j, right? Then the k component, we have plus sine t k minus e to the t cos t k, right? So this is what we have for the u prime of t cross v of t, right? This is what we have, okay? Next, we have to find the second part, which is the u of t cross v prime of t, right? So we're going to say that, this will be equal to u of t is here, right? So we have I, d, k, and our t, e to the t, t squared, and then v prime of t is negative sine t cos t and 0, right? So this is what we have. So what we need to do is to find the determinant, right? So we have I into e to the t cos t, e to the t squared 0 minus j into t negative sine t, t squared 0, then plus k into t negative sine t, e to the t cos t, right? So this is what we have. So we can say that this is equal to I into what? This times this will be 0, right? 0 times e to the t is 0. Okay, so that part is gone. Then minus t squared cos t for the I component minus j into this times this will be 0. Okay, then that one is off. So we're going to have negative sine t times t squared is negative t squared sine t, but there is negative affecting that diagonal, so it's going to be plus, right? So we have t squared sine t, right, plus k into t cos t plus e to the t sine t, right? So this is what we have for the I component, this is what we have for the j component, and this is what we have for the k component. So we have all that we need. So what we have to do next is to add them, right? So we're going to add this to this. Okay, so we're going to say that this is equal to the second part, right? So we're going to add it to this. So plus negative t squared cos t I negative t squared sine t j plus t cos t k plus e to the t sine t k, right? So finally, we can say that we have this is I and this is I, this is I. So we combine them. So we're going to say that we have e to the t minus 2t sine t, right, minus t squared cos t or I, right? So we have that. Then we come to the j component. This is j as well. Okay, so we combine that. So we're going to say that plus into 2t, right, plus into 2 plus into negative 1 plus 2t cos t, 2t cos t or j, right? Then we come to the k component where we have plus sine t minus c to the t cos t. Then we add this. The j component, we have to add this one as well. So minus t squared sine t all j, right? So we are done with the j part. So the last part with the k is going to be sine t minus e to the t cos t plus t cos t plus e to the t sine t or k, right? So the k components, we have 1, 2, 3, 4. 1, 2, 3, 4. Great. So let's simplify that here. Let's simplify that here. So we can say that we have this to be equal to e to the t, right? E to the t, then minus 2t sine t minus t squared cos t or I, right? Plus into -1 plus 2t cos t minus t squared sine t or j, right? Plus sine t, okay? Sine t sine t plus sine t e to the t minus e to the t cos t plus t cos t or k. Okay, so this is the answer that we have, but let's check the options, right? And represent the solution as to how it has been represented here, right? So we can say that we are factoring this out. So the I component, we can say that we have big brackets, right? Big brackets e to the t, right? E to the t minus into 2t sine t plus t squared cos t, right? Or I. Okay, that is it here, right? That is it here. Okay, then the j component, we can say that we have plus into 2t cos t minus 1, right? 2t cos t minus 1, right? I just interchange the position of this and this. So 2t cos t minus 1 in one bracket minus t squared sine t or j, right? Then the last component, which is the k, we can say that we have t minus e to the t minus e to the t cos t plus 1 plus e to the t sine t. Okay. Right? I just factored out, we have negative e to the t cos t and we have positive t cos t. So I factored cos t out and I have t, minus, okay, t minus, when this cos here, it comes here, we have this right here, and then when we expand this, we have this, okay? Then this as well, we have here, when we bring the sign inside, we're going to have this, and then when we bring the sign inside, we're going to have this. So that is what we have here, okay? So this becomes our final answer to problem number 17. Okay, this is the final answer to problem number 15. Okay, so let me summarize everything for you. If you have u of t, you have one function, another function, and you want to find a cross product, okay? Don't forget, in cross product, then you are going to apply product rule, okay? So once you are going to apply the product rule, please don't misarrange the differentiation, okay? Don't misarrange the differentiation, because when you have u and v and you are differentiating this, you have to differentiate the first term first, right? So differentiate the first term, maintain the second term, plus maintain the first term, differentiate the second term. If you follow this, okay, if you follow this rule very well and you go to cross products, you won't have a problem, because in the cross product we use matrices, and matrices really appreciate order. Don't forget, if you write u prime of u prime times v is not the same as v times u prime, right? This is not the same. When you go and present this information in a matrix, this is not equal to this. So please, every time, if you have two functions and you are differentiating, okay, the product of two functions and you are differentiating, make sure you differentiate the first term first, then maintain the second term, then after you maintain the first term, they differentiate the second term. Because if you send that to matrices and you don't follow that order, you are going to have a problem, because position or order really matters in matrices. So that is the end of question number 15. Okay, this is the final answer. Okay, so let's move on to question number 16. Okay, with question number 16, question number 17, question number 18, 19, and 20, I'm just going to give you a summary or an overview of how you go about it. Okay, then that will call it for the end of this lecture. Okay, so let's move on to question. Okay, so with question number 16, if you have to find a maximum directional derivative of a particular function, what they are trying to ask you is that find the magnitude of the gradients, okay, of that particular function, okay? And this is of several variables, x, y, and z, 3 variables, okay? So we find the derivative of this function with respect to each of the variables, okay? So once you have the derivative with respect to x, y, and z, substitute the point in it, okay? Then when you substitute the points into that, into x, y, and z, then you have what? You have the evaluated what? Gradient. Okay, so once you have the evaluated gradient, find the magnitude of that, and that becomes your maximum directional derivative of that particular function. So, this is the function that we have been given, f of x, y, and z equals e to the x sine into y plus what? Z, right? So this, you find the derivative of it with respect to x, and that you are going to have the same function, right? You are going to have the same function. And then you do the same thing with respect to y. So you're going to differentiate this with respect to y. So you're going to have, when you differentiate this, you're going to have cos into y plus z e to the what? X, right? Then with respect to x, you're going to have the same cos, right? So with respect to x, you're going to have z, you're going to have cos into y plus what? Z e to what? X. So this is what we have for the derivatives. So once you have this, substitute the points into each. Okay, so fs at 0, pi on 2, pi on 2 will be equal to, when you substitute pi here, you know x is 0, y is pi on 2, which is 90, right? You know pi on 2 is 90. So x is 0, y is pi on 2, and z is also pi on 2, right? So we're going to do that substitution. You do that substitution here. So when you substitute 0 here, you're going to have 1. 1 times sine 90 plus 90, it becomes what? Sine 180, right? Sine 180, okay? And that is basically 0. Sine 180 is 0. So we have the fs at this point. Fs at this point will be equal to what? 0. Okay? The fy at this point, when you substitute 0 in place of this, you have what? 1. When you have pi on 2, which is 90, 90 plus 90 is 180. Cos 180 is negative 1. So we have negative 1 here. Okay? Then you substitute 0 here, you have 1. Right? 1 times this. So, you know, y and z is pi on 2, which is 90 plus 90. So it's going to be 180. Cos 180 is what? Negative 1. So negative 1 times 1 becomes negative 1. So fz at the same point, is also what? Negative 1. Okay? So this is what we have. The gradient for the function is equal to 0, negative 1, and negative 1, right? So what we need to do to get the maximum directional derivative is to find the gradient of this evaluated gradient, is to find the magnitude of this evaluated gradient. So the magnitude of this will be equal to square root of 0 squared plus negative 1 squared plus negative 1 squared, and that is negative 1 squared plus negative 1 squared. That will be equal to 1 plus 1. Okay, so we're going to have square root of what? 2. Okay, so that means that the maximum directional derivative of this particular function at this point is square root of 2. Okay, don't forget, square root of 2 can be expressed as 1 over square root of 1 over 2. So this can be expressed as square root of 2 can be expressed as 1 over square root of 1 over 2. So these are all the same. Okay, so that is question number 16. Please note that if you are finding for maximum directional derivative, all you need is to evaluate the function that you have been given, differentiate each component, right? With respect to x, with respect to y, with respect to z, as to how many variables we have, differentiate with respect to each of the variables. Once you are done with that, then evaluate these functions that you have with respect to x at those points, with respect to y at those points, and with respect to z at this point. Once you have these points, find the magnitude of that. Then you have the maximum directional derivative. Very simple, right? So let's move on to question number 17. Question number 17, this question is of the same form as the earlier one, the question number 13, right? You know that if you have a function like this and you want to integrate or you want to evaluate, what you have to do is deal with it term by term or component by component, okay? This is I component, this is J component, this is K component, okay? So with the I component, you see that we have negative of 1 minus 4t over 2t squared minus t all squared, right? With respect to t, okay? So this, when you see a function like this, right? When you see a function like this, it's basically telling you that this is a tangent function, okay? This is a tangent function. Don't forget that when you integrate tan, when you integrate 1 over 1 plus u, you have the tangent inverse, right? So this is, of course, of this form, okay? This is, of course, of that form, right? So this can be expressed as 1 over 1 plus u squared. Okay, so we are going to use that idea to find the integral of this particular function. So let's go. So here, let's say that our u should be equal to 2t squared minus t, right? So we can say that the u should be equal to what? 4t minus 1, okay? We said u should be equal to this function. So we had 2t squared minus t here. And when you differentiated it, we have 4t minus 1, the t, okay? So now let's make the t the subject. So the t will be equal to the u over 4t minus 1, okay? So this is what we have. Okay, so we are going to use this function and substitute here, and we already know that this whole function is what? U. So we are going to say that integral negative, so negative of 1 minus 4t all over 1 plus, we know that 2t squared minus t is u, so we have u squared, okay? There is 2 here, so u squared. Then our t is now du over our 4t minus 1, so we have du over 4t minus 1. Okay, so don't forget this numerator, negative 1 minus 4t, can be expressed as 4t minus 1, right? So we go ahead and do that substitution here. So we're going to substitute this in place of that, okay? So we're going to have this here, 4t minus 1 over 1 plus u squared times du over 4t minus 1, okay? So this cancels this here. Then we have integral 1 over 1 plus u squared du, right? So now we have broken the thing down, okay? So it's very simple now. So you know that the integral of 1 over 1 plus u squared du is tangent inverse, okay? So we're going to have tangent inverse of u plus a constant, say c1, okay? Now don't forget that your u is 2t squared minus t, okay? So we are going to do that substitution in here, so we're going to say that tan inverse of 2t squared minus t plus our c1. Okay, so this is the I component. Okay, this is the I component. So this is what we have for the I component. Don't forget that tan inverse of u is the same as arc tan of u. Tan inverse of u is the same as arc tangent of u. Okay, so if you see this or this, they are all correct, right? So we have the I component to be tan inverse of 2t squared minus t plus a constant, say c1. So we go ahead with the second component, which is the j. Then we integrate that. Okay, so we're going to integrate that. So integral of t e to the negative 2t j, right? So this is what we are going to integrate the next. Don't forget, if you have two functions that are multiplying and you want to integrate, use by parts, right? And by parts here is going to make our work so voluminous, right? And we are dealing with time. So we are going to use what we call the tabular method or the DI method in here. It's going to make the work so snappy, right? So we say that u should be equal to the differential function, the function that we can differentiate to a constant, and then vn will be the function that we can integrate to whatever it will reach. So we represent the u to the function that we can differentiate, okay, to a constant. So u and vn. So u here will be the t, okay, the t here, and the vn will be negative 2t. So we differentiate t and we have what? 1. We differentiate 1 and we have what? 0. We integrate e to the negative 2t and we have negative e to the negative 2 over 2, right? Negative e to the negative 2t over 2. Then we integrate again. Then we're going to have e to the negative 2t over what? Positive 4, right? So this is what we have. So what next? You know, the integration by part, the sign is plus, minus, plus, and in that order. So we're going to use that same signs on this. So we say that this to this plus, this to this negative, right? So we're going to say that our j component will be negative e to the negative 2t over 2, right? Negative 2, negative t, negative t e to the negative 2t over 2 minus negative e to the negative 2t over 4, right? So minus e to the negative 2t over 4 plus a constant c1, right? So this is what we have for the j component, negative e to the negative 2t over 2 minus e to the negative 2t over 4 plus a constant, say c2, right? So this is what we have for the second component. We do same for the last component, which is the k component, okay? So we are going to integrate that as well. So we integrate the last component, which is the pi k dt. So we have pi dt here. You know, when you integrate pi with respect to t, we have what? Pi t. You know, pi is a constant. Then we multiply by the t. So we are going to have equals pi t plus a constant, say c3. So this is what we have for the last component. So you know that C1, C2, and C3, they are all constant. So we can say that C should be equal to C1 plus C2 plus C3. Okay, so that is what we have. So we're going to say that this plus that plus a constant c. Then that is the evaluated what for evaluated solution for this particular integrand. So we're going to say that our final solution is equal to tan inverse of 2t squared minus t plus the second component is negative t e to the negative 2t all over 2 minus e to the negative 2t all over 4. This is I, this is j, plus pi t plus a constant of integration c. Okay, so this is our final solution. This is our final solution. So let's check how it was presented here. Okay, so we can decide to factor out this. So we can say that the first component, tan inverse of 2t squared minus t, or I, minus, you see, half is common to all these items, and e to the negative 2t is common to all as well. So we factor out minus half e to the negative 2t. So we're going to have minus half e to the negative 2t out. Then we say that we have t plus half inside. Okay, t plus half inside or g. So that is the j component, and the last component, which is plus the pi t plus a constant c. So this is our final solution to the problem given, right? So, whenever you have a problem of this form, just take it component by component. And once you have not forgotten about your integration techniques, your differentiation and integration techniques, you are good to go, right? So look, if you forgot about your integration techniques, my link is right there at the description for a recap. Okay, so with question number 18, this is what we have. If r of r is equal to this, we want to find the r, right? That is a total differential. So this is basically a vector field. So if you are given a vector field and you are to find this, all we need to do is to find the total differential, right? So we will find the total differential or derivative of the vector function. So we are going to find the total differential or the derivative of the vector function. So here, what are we going to do? We're going to differentiate this function totally, right? So differential of the function equals, we differentiate with respect to x times the x, straight the x, plus, that is for the first term, okay? Because the first term we can see y, we can see x. So with respect to x and with respect to y, okay, so times straight y. Okay, so this is for the I component. Then with the j component, we differentiate with respect to z and with respect to y. So partially with respect to y times straight y plus with respect to z times this, right? So we have this here, okay, plus the last part with respect to x and with respect to what, z. So we're going to have with respect to x times the x plus with respect to z times the z, right? And that is the key component, right? So this is all we need, okay? This is all we need. So we are going to differentiate the first function, which is the first component, with respect to x times the total differential of the what? The dx, plus partial with respect to what? Y times the total differential of y. Okay, so let's do it term by term. So let's say that the f for the first component, we are differentiating with respect to x. So with respect to x, we are going to have what? Cos x e to the what? Y cube, right? Then this times the x, right? Plus with respect to y, okay? With respect to y, differentiate what is on the exponential function. We're going to have 3y squared e to the y cube. Then we have our y, the sine x, dy. Okay, so let me write it here. Cos x e to the y cube dx plus 3y squared e to the y cube sine x dy. Okay, so this is the I component, right? And this here, we can do something about it, okay? You know that this here, sine is here and cos is here, okay? So what do you think? You know that tan is sine over cos, right? So when we factor out cos, then we can say that when we factor out cos, we have cos x into what? Let the big bracket come here, cos x into okay. So we factor out okay, so we factor out cos x e to the power y cube into the x over 3, right? Plus y squared tan x dy, right? So this is what we can do, okay? You know, when we send this back, then we have what is here. Then we send this back to here, then we're going to have what? Cos x times tan x, right? And you know that tan is sine over cos. So when we express in that way, then the cos will cancel the cos, then we have the sine back, right? So this is basically what I'm talking about, times tan x, right? And you know that tan is sine over what? Cos. So times cos, this cancels this, then we have this back, right? So that is how we can express the y, the I component, right? So we say that 3 cos x e to the power y cube into the x over 3 plus y squared tan x dy. This is what? The I component, right? So this is the I component we have here. Okay, so let's move on to the J component. So we are going to apply that same principle to the j component. Okay, so let me erase the I components. So I'm taking off the I component, right? So with the j component, we differentiate with respect to y. When you differentiate tan, you have what? Okay, let's start with the z squared first. So we differentiate z squared, we have 2z, then we maintain the tan y. Then this is times z, right? Plus we differentiate tan y, that is sec y, right? So we're going to have z squared sec y dy, right? And that is the j component, right? And this j component, we can express it as z squared sec y dy plus 2z tan y dz, right? So let's write this now. Then we move on to say that this is the same as z squared tan y into sec y cosec y dy plus 2 over z dz or j, right? So this is the j component, right? Don't forget that when you expand this back, you get this back, right? This here, okay, sec y cosec y is the same as 1 over cos y times 1 over sine y, right? So this and this here, we get back to this. Okay, so that is basically for this expression. Okay, so this is our I component, this is our j component. So let's try and deal with the last component, which is this. Okay, so we are going to differentiate with respect to x and z. So with respect to x, we're going to have 2e to the 2z cos z dx plus, with respect to z, we are going to differentiate cos, right? So it's going to be negative sine. So we're going to have negative sine z e to the 2z dz. And this is the j component, right? So this is what we have for the j component, and this is what we have for the I component. This is what we have for the I component. Okay, so the j component or the k component can be expressed as 2e to the 2z sine z into cot z into cot z dx minus dz over 2 or k, right? So this is what we have. So this has been expressed in this form. So we're going to combine, or then we can say that we have our dr, okay? So we're going to combine, or so we have our dr will be equal to the I component is 3 cos x e to the y cube into the x over 3 plus y squared tan x dy, or I, then the j component is right here, plus z squared tan y into sec y cosec y dy plus 2 over z dz, or j. Okay, so let me add the k component. Then so the k component is plus 2 e to the 2x sine z into cos z dx minus z over 2 dk, right? So this is the I component, this is the j component, and this is the k component. Okay, so that is the R. Okay, so whenever you are given a vector field function and you are asked to find the R, what you need to do is state the total differential formula, right, with respect to the variables. Okay, so you know this in here, the first component we have x and y, so you just say that with respect to x, the x, plus with respect to y, the y. So this is the I component, right? Then you come to the j component, you say we have y and z, so you say with respect to y dy plus with respect to z dz, right? Then that is the j component. Then you come to the k component where we have z and x, so that is with respect to x dx plus with respect to z dz, right? So this is the k component. So we have I, j, and k. So you just find the differential with respect to each of these components, then you combine them, and that becomes your dr whenever you are given a vector field function. That is the process. So please don't forget. Now let's move on to question number 19. Question number 19, I'm just going to give you a brief and a clarification, and then you do it by yourself. And question number 20 as well, I'll just give you a brief clarification, then you do it by yourself. Okay, so with question number 19, we have been given this particular equation, okay, and we have to find a parametric equation. Okay, so this is something that myself, when I saw the question the first time, I was like, wow, what kind of lengthy equation is this? And we had to find a parametric equation. So I was like, no, this. But I gave it a try and I was able to do it. So this as well, I want to give you, give it out so that you give your trial, right? I'll leave the solution, right, so that you work towards it. Okay, so this, what you have to do first is to group the terms. Okay, so we have x, we have y. Okay, so group them term by term. Okay, then when you are done, you find use the complete of method of completion, right? That kind of thing, method of completing of squares, right? So you group them, x, you group y, so you say that x 9x squared minus 722x into 1, then plus the second part minus 4y squared plus 8y at one portion plus 176, right? Then use the method of completing of squares, right, to deal with this. Okay, so you'll be having some factorizations. That process will lead you to the solution. Okay, so let me leave the final solution to you. So the solution to this particular problem is 2 sec squared t cos t plus 4 and 3 tan squared t cos t cot t plus 1. Okay, so this is the parametric equation. So I would like you to work towards this particular solution. Okay, whatever the case be, leave your comments at the comment section. All right, so let's move to question number 2. And this is the last part of the question. Okay, this is the last part of the question. So this as well, I want to give it to you as a trial. Okay, but I will leave the final solution. Anyway, let's go into it. Then let me give you a summary. Okay, so with question number 20, we have to determine the domain of this particular vector valued function. Okay, so once you hear the word domain, then begin to think of a function where you look at the function and look at what will make the function not to be undefined. Okay, look at the function and look at where the function will not be undefined. Okay, where the function will not be undefined. So look at the I component. Okay, you see that we have ln into 5t minus 1. Don't forget, any argument that is inside the ln function or the natural logarithmic function, make sure that it is greater than 0. Don't forget that. Any argument that is inside the natural logarithmic function should be greater than what? 0. So this is what you are going to do. You know that 5t minus 1 is an argument in the natural log function. It should be greater than 0. Okay, so we say that t is what? Greater than 1 on 5, right? So this is what we have. Okay, what then do we have to consider? We have to consider the denominator. Okay, mainly when we talk about domain, we are looking at mostly the denominator, right? So that the function will not be what? Undefined, because when you have 0 there, the function is going to be what? Undefined. But this case, we have natural log in it, right, at the numerator. And in the natural log, we have to make sure that it is not taking any number that is less than 0 or equal to 0. It has to be greater than 0, right? And that is positive. So we have checked for that, and we are saying that t should be greater than 1 over 5. So anything we put here should be greater than 1 over 5. Then we can have a proper function. So in here, we have square root of 1 minus t squared. And that any argument that is under the square root sign should also be greater than 0. Right? So we have 1 minus t squared should be greater than 0. So we have t squared should be greater than what? 1. So we have t to be greater than what? 1. Right? We have plus or minus 1, but we are not going to consider the minus, right? So because when we consider the minus, we are going to have 1 squared, negative 1 squared is negative 1, right? And when you put 1 minus 1, you have what? 0. And root of 0 is what? 0. And when you make it this form, you're going to have undefined. So we are not accepting the negative, but we accept what? Anything that is greater than what? 1. So we are accepting anything that is greater than 1, and we are accepting anything that is greater than what? 1 on 5. We don't even talk about this because there is nothing like a fraction, right? That will make the function undefined. we are mostly looking at the I component, right? To this particular question, the domain is focusing on the what? The I component. So anything should be what? This greater than these two values. Okay, so that is going to be the what? The domain for this particular function. Okay, so we say that t is such that t is what? T is T is such that we have 1 on 5 less than T less than 1, right? So this is going to be our domain for the function. All right, so this is the domain for the this particular function that we have here. Ladies and gentlemen, we have really tried our best, and we've solved all the questions from number 1 to number 20. Please keep learning and don't forget to subscribe, share with your mates, comment. Please, it really helped me. Comment as you watch. Stay inspired until the next video. Bye bye.